Hello everyone. Am I audible? Okay. So hello everyone. This is Annu. I'm PMRF PhD scholar at IIT Hyderabad. So I will introduce myself as I will be the live instructor for this course for the next 3 months. So this is Annu, PhD scholar at IIT Hyderabad. So as part of this course, I will be taking the live sessions every from Saturday from 3 to 5. And I'm very active in LinkedIn and my email ID. So for any doubt, you can just contact me at uh, this email address. Okay, so basically, I will be going through the course content of every week, like as you might have taken this course as part of your BTech curriculum, or maybe MTech, or maybe you want to learn about the cellular and wireless technologies. So in this course, basically we will be going through 2G, 3G, 4G, 5G, and what are the characteristics of channel and how to identify the channel. We will be going through that, and I will be going through the summary of every week lectures taught by Professor David Koipillai sir. He is one of the very good faculty. During my time also, I studied from him. And I'm currently doing a PhD from IIT Hyderabad. So we will be solving some questions, most probably the last year questions we'll be solving, and we will identify we'll be identifying some challenges, and basically if you are having some doubts in how to solve the problem, so I'm here to help you. And the live sessions are meant to be like this, like it should be very much interactive. It should be it should be a revision for you, like as you know, you might have gone through some lectures, or maybe not. Even if you don't want to go through the lectures, I'm here to revise some concepts. And as week one was more theoretical, so we will not be going very deep into that. But yeah, I have some things for you to discuss, like some Python simulations. I will create some more beautiful content so that you guys will get interest in wireless communication technologies. So this is all about me. Since this was the first class, so I'm introducing myself. I would like to know about the audience here. Like, can I get to know about Minoj? Hello, Vinod. Can you speak about yourself?
Yes, ma'am. Am I audible?
Yeah, yeah, you're audible.
Myself, Vinod. I am currently working at ISRO, and in fact, I am doing my PhD in IIT Kharagpur Aerospace Department, and this I have taken as a part of my coursework in the first year.
Great. Ah,
Yeah,
that's great. We are working in ISRO. That's great to know. Nice, very nice.
thank you.
Yeah. Hi, Sandhya. Sandhya. Okay. Hi, Aftab. Aftab Alam. Okay. So no problem. We will be going through this course, and hopefully you guys enjoy. And if you have any doubt, you can just reach out to me at this email ID. And I'm also very active in LinkedIn. So you can contact me over LinkedIn if you type Annu IIT Hyderabad. I think you must be getting my LinkedIn ID. And I would love to connect with you personally also at any point of time. So yeah, so week one. So basically week one was on the overview of cellular 2G, 3G, 4G, and 5G technologies. And there we found out what are the basic, what are the main motivation for the advent of the cellular technologies, and what actually drives this 2G, then how 2G is different from 3G, then how 3G is different from 4G, and similarly 5G is different from 4G. Like if they are existing cellular technologies, why this 3G is needed, why this 4G is needed, and we all are talking about 6G. Why 6G is needed? So the question here is why 6G is needed. So the point is like since the number of users are increasing so much and we are having the limited amount of spectrum. So the spectrum is actually very scarce. What do you say? You are having the spectrum given by the ITU, International Telecommunication Union. Okay, and then we will be giving the spectrum or the allocation of spectrum. This is the international way I'm telling because here the wireless communication technology is taking care internationally all around the world. And then the spectrum allocation will be done by some of the working groups of this ITU. So in this working groups, we are having 3GPP working groups. In the 3GPP working group, the spectrum will be allocated. So once the spectrum is allocated, then we need to use the spectrum very efficiently. That is called resource allocation. So in the resource allocation, the users are more. For example, if you talk about what is wireless communication. So if you talk about suppose this is a base station, and the base station is like here, the base station consists of the radio unit, it consists of baseband unit, then it consists of some higher layers, and finally it connects to backhaul, it is connected to a core network. So the core network is actually somewhere sitting in the cloud. Okay, so I will tell you the basic uh, picture of wireless communication. So yeah, we are having the base station, as you all know, and this is connected to an antenna, maybe some horn antenna or something like that. Okay, and then through optical fiber, we are having core network. So this base station is called G node B in 5G. It's called E node B in 4G. And okay, so I'm talking mostly about 4G and 5G, and in 6G we will call plus some enhanced. This is enhanced Node B, and this is the next generation Node B. So in base station we are having three main components. Here somewhere here it is RU. This is a radio unit. Somewhere here we have baseband BBU, base band. Okay, so as we know, there's also a term called Open RAM. So what happens exactly is between RU and BBU, it has to be from the same company, maybe same Qualcomm or Nokia. So we are basically making it open. Once this is open, like it is in the software, then it is called Open RAM. Otherwise, it is called RAM. This is called Radio Access Network. Okay. So suppose any user wants to connect. This is user, this is mobile phone. Then if any user wants to connect to a base station, or suppose a user wants to call any other user two. How these two will get the connectivity? Like it has nothing. So as we know, we are having a SIM. So SIM is there. So in SIM, they were having SSID. Through this SSID, it will find out the PCI, so physical cell information, where it is lying, and then through this base station, okay, Like it will broadcast, okay, I'm here, I'm here, I'm here, suppose I'm here. So it will broadcast some primary synchronization signal, okay, some synchronization signal or some signal you assume. Then the base station will know, okay, you are here, physical cell identity number, you are here. Then you will, the base station will identify, okay, the other user is here. So it will give the resource block. The resource block is given by base station. Okay, you take this resource block, this you take resource block. Now the resource block is what? So starting only, I told this is spectrum. Spectrum means what? In it is time, it is frequency. We are having time, frequency, and it is split into some square forms waves. Okay, so suppose it is 20 megahertz of bandwidth. So this spectrum, okay, the user one will be given this spectrum, user two will be given this spectrum, and then if they are given the spectrum, then they are allowed to communicate. Because suppose I'm speaking to two different person. Then I'm giving, okay, you take one time slot. I will speak to one time slot to Vinod. I will take speak to Aftab in other time slot. So that's how I'm dividing. But in wireless communication technology, basically in 5G, the division of the spectrum allocation is OFDM, orthogonal frequency division multiplexing. If you talk about 2D, 2G, so there are some different multiplexing techniques are used, because at the same time we are having multiple users, and we need to make sure that, okay, you will be also getting some resource block, you will be also getting some resource block. At the same time, they should not interfere, because we are having lot of connectivity. And what is our aim? Our aim is to have as many as connection as possible in a proper without any call drop scenarios. So in order to make sure, the base station is the one who takes care of that. And the base station is having the control of the resource blocks or the resource grid. And if you talk about in some other scenarios, that's how when a vehicle moves from one cell to another cell, if there's some, it is lying in the edge, then the call suddenly drops. And if it goes to another cell where the connectivity is more or the base station has good reach, then the connectivity suddenly rises. Similarly, if you are standing in, suppose, in a room or in your home, then it doesn't connect. Then you try to go out. Okay, okay, okay. Now it is coming. The signal is coming. The signal is coming. The signal is what? The signal is governed by the base station. So here we are talking about the base station, which takes care of what. So that's the beginning of wireless communications, and the world is moving towards that. And I hope in the future we'll be having 6G, and that should be driven by India. So yeah, so basically I will just go through some brief of every slide. Then we will solve some previous year solved problems related to week one. Similarly, we will continue the same for the other weeks, such a way that we have all the concepts in our hand or in our mind, and at the same time we should be able to solve the problems related to it. Okay, so the JC Bose was the one who began all those things. Like, it's not that important, so I'm just moving towards it. But yeah, it's it. Whenever we talk about the cellulars, how it begins, so we should know some of the dates. Like in 1895, like when we didn't born yet, this JC Bose demonstrates the wireless operation at 60 gigahertz. Can you imagine? The 60 gigahertz is huge. Yeah, 60 giga is huge. Why I'm telling 60 giga is huge? Because what is our voice frequency? Have you ever wondered what is our voice frequency? Though I'm speaking at voice is 3.3 kilohertz. So 300 hertz, so 3.3 kilohertz is actually the voice frequency. Now this is in practice, like, or the analog frequency. And also the another concept is like whatever the physically occurring signals are analog in nature. And if you say what is signal, then a signal is the change in the amplitude with respect to time, or the change in any physical quantity with respect to time. So that is a signal because it is changing with respect to time as the time changes. So that is signal. Okay, any physical quantity, it can be temperature, it can be pressure, it can be anything. Okay, so the voice is having this frequency. Now I want to speak uh, through a phone. So what it does, basically, a normal mobile phone, what it does. The normal mobile phone, just adding someone. Normal mobile phone does the modulation in process. So the modulation is what? Modulation is nothing but it changes one frequency to another frequency. And what changes, like it's just a mixer which just changes some frequency to some other frequency, or it is also making sure it should be higher frequency. So what it does is, if we convert to higher frequency, then according to this formula, c is equals to mu lambda. What it does, mu is nothing but frequency, and lambda is equals to c by mu. C is fixed, it is the speed of light, 3 into 10 to the power 8 meter per second, and this mu. So lambda is inversely proportional to mu. And as we know, all the antennas design is directly proportional to antenna height, is directly proportional to lambda by 2, or you can say directly proportional to lambda. So in our phone, can you imagine, can anyone guess in our phone how many antennas are there? I am having a 5G phone. I'll show my 5G phone. Just a second. How many antennas are there? Just guess. So I'm having this phone. This is Realme, some model is there. It's having 5 antennas. So this small phone is having 5 antennas. Why? Because it's a 5G phone and it operates at FR1, which is from up to 7 gigahertz, and FR2 is up to 300 gigahertz. So 5 gigahertz, if you convert to frequency, sorry, lambda, then it will be very less. Okay, so that centimeter antennas are embedded into this phone. So that's why we need to make sure, and we want as compact devices as possible. So that's why modulation is done. So uh, that's how the things got changed in different generations. So I didn't remember this word. This is the FCC, Federal Communication. Some full form is there, FCC. So that allocates bandwidth for the cellular systems. Federal Communication Commission. So this only allocates Federal Communication Commissions. Okay, this you should know as a communication engineer. You should know that this FCC what it stands for. So yeah, so in 1G it was the Nordic mobile telephone, whereas in 2G it was GSM. You should know only the terms. I'm not talking. You should know very deep. The deep things will come into the picture of this course. Basically, this course talks about the wireless channel. It doesn't talk much about the technology, modulation, demodulation. For that, the courses are analog modulation, amplitude, analog modulation, digital modulation. So I want to know how many of you have done this digital modulation course? Vinod, have you done this digital modulation course?
No, ma'am, I have not done digital modulation course.
Digital communication or digital anything?
No, digital communication only as part of my undergraduate course I have done, but not
Look, like you are undergraduate in?
electronics and communication.
Okay. That's great. Like you are working in ISRO, and right? You are working in ISRO.
Yeah, correct.
Okay. From how long you working?
For past around 18 years.
Oh my God, that's very great. Like you want to, like you want to learn at this time. That's great to know. Okay, that's great to know. That's how it should be. Someone joined. Mm. Okay, so yeah, so this was the scenario, and in India we are having TRAI, and if anyone wants to continue and want to know more about the India connectivity and all, I would like to ask you to please follow TRAI website and also LinkedIn page. You can all follow that gives a quarterly report of performance indicators. And India wireless situation is like cellular market is going very high, so it cost crossed, like we are having so many suspicions that the India is growing in population, and you will rarely find anyone who's not having a mobile phone, and those who are not having a mobile phone is very less in number, in fact negligible. And those who are having the phone, they must have internet connectivity, and the internet connectivity will be only given by this our communication standards. Okay, so these are the mobile scenarios, and yeah, this is very important as part of this theoretical course. Theoretical question can be asked from your exam point of view. So basically we're having these three family of wireless networks. So this radio access network is of prime importance. Sorry, regional area network. This is wide area network, the metropolitan area network, local area network, personal area network. So these are some area of networks, and in this regional area network, we're having satellite mostly because it covers up to higher range. And in wireless area network, we are having this wide area network. Sorry, this is wide area network. And in this wide area network, we're having wireless, which is cellular networks. And its GSM is known to 2G. CDMA is actually 3G and 2.5G and 3. These are the CDMA. Meanwhile, we will be having 4G and 5G that we will talk about. These are some Wi-Fi technology. And this is also one of the Wi-Fi technology, like there are A, B, C, D, E, different standards are there. And India has all scenarios. That is one of the biggest thing. So also, we are also having a glimpse of the evolution of cellular. Why? Because as we know, the capacity, like the spectrum, which is increasing in number. That's why, if you wonder, in 2G we are having less frequency, whereas in 3G we are having higher frequency, 4G more high, 5G more high. The frequency range is high in number, but at the same time, when the frequency increases, the coverage decreases. Why? Why it decreases? Because C is equals to mu lambda again. When frequency increases, the lambda decreases. Okay. And somehow the distance or the coverage of connectivity is proportional to lambda. Also, antenna size is proportional to lambda by 2. So that's how this is the benefit, but this is the disadvantage. So here we will have massive MIMO and different diversity technology to combat this situation. Like the coverage is less because here, if you see in 2G, only one antenna was there to cover this. Whereas in go to 5G, then small cells, very small antennas are there, but we need to have more antennas. So the question is like, also that the only difference between cellular and Bluetooth, Wi-Fi, sorry, ultra wideband or Zigbee, these are some other IoT based technologies. These are unlicensed. Okay. Whereas cellular is governed by FCC, that is license. Like we have to take a license, then only we can broadcast a message or used that's why all the telecom operators are having license of cellular technology like 4G, 5G, just 2G, 3G, 4G, 5G are the licensed technology, whereas Bluetooth, like you can transfer data through Bluetooth, these are unlicensed. Similarly, there's a ultra wideband, similarly there's a Zigbee. These are some unlicensed technology. And all the unlicensed technology will come into what? The question is, it will come in personal area network. as of now, unlicensed device. And this is also written this, there are different data rates for these all technologies. Okay, so I will not go through this. This I've already talked a lot in the lectures. The lectures of the week one are little much more theoretical, but I would not ask you to skip at least from second lecture. You can skip first lecture, but from second lecture you can closely look into it. And these are some very good lectures, and where they like David sir is one of the big, very good professor I have so far encountered. So you'll get to know a lot about this course. And in this live session is basically my aim is to since many people joined now, so I'm just telling again, the live sessions are meant to be as interactive as possible. So whatever doubts you're having while you are going through the lectures, for example, in problem solving, for example, some theoretical concept, for example, some big concept or some logical concept, then you are free to discuss here. And I've also given here my email ID, so I would love to discuss more about your personal doubts also. So whenever you are mailing me at this email ID, I can be prepared the next lecture and we'll discuss thoroughly about that question. And this is how I used to do in my previous TAships. So I would like to connect with you with your doubts. That will be best to do that. Okay, so I'm just moving through some more things which I really want you to go through that. So one of the thing is like why we want 5G and what is there after 4G, as we know. So the world is having a buzzword called 6G. So what exactly is 6G? So I told the 6G only differs from the technology perspective. Everything is same and the spectrum is different. Like spectrum is not yet allocated, but 5G has two spectrum, FR1 and FR2. You can just check into the net, the exact values. It's in gigahertz. Up to 6 gigahertz, it is FR1. After 6, it is FR2. And up to 300 gigahertz. Okay. So these are some things. The 4G was more focused on spectral efficiency, interference mitigation. And in 4G only, we are having OFDM. So that was one of the thing like how it differs. Now, this I would like to discuss a little deep. Like a transmitter. Transmitter is something which transmits any information. So what exactly it does? So in practice, what we are having, we are having antenna. And what antenna does? It converts electromagnetic wave to electromagnetic wave to electrical signal and vice versa. Okay, so it's actually a transducer that converts two different forms of signals. But if you talk about the transmitter, suppose a phone is also one of the transmitter that transmits signals. So it goes through several steps. So one of the step is suppose a source is given. So any source is given, any information is there, and that information, suppose I'm speaking message. So the message needs to be compressed. Like it cannot, since I told you the bandwidth is very scarce, so we have to utilize the resource in a proper way. So that is called source coding. Then again, the information should be very much private. The privacy should be maintained. That is called encryption. Then it has to pass through some error protection. And that error protection, for example, we are having 01010. And after compression, it is 010 only. So after this, once the privacy is maintained, some key and values are maintained, then you will do the error protection. So in order to protect the error so that the error is not there, you will sometimes repeat this information to several times. Suppose 3 times. Okay. Then after this, you will modulate. So the modulation is again, I told that it's convert from one frequency to higher frequency so that the antenna side reduces. So there are some different types of modulation. It's another topic in digital communication. But yeah, it does it's actually to not to transmit the message. In order to transmit the message, is as I told that I am in the frequency range of 3.3 kilohertz, so that cannot go up to a certain limit. So in order to that, we will have the carrier wave. The carrier signal will be embedding that information and it will be transmitted to higher frequency, and that way the modulation is done. So there are different types of modulation like analog modulation and digital modulation. So so in analog also we are having amplitude modulation, we are having frequency modulation, we are having phase modulation. In digital modulation, we are having BPSK, QPSK, QAM, PAM, PWM. So there are different modulation, different types of modulations are there. Then after modulating it, since it reaches to a different information, it's so that it boosts. So we have to transmit filtering to make the transmit packet as compact as possible. So that is called pulse shaping, and that is called spectrum shaping also sometimes. So as information source is always analog in nature. So after this, it converts digital. Okay. So here you are talking about digital, 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 digital. So at the receiver, sorry, this is transmit only. After pulse shaping and all, you will convert digital to analog. Then it converts baseband because this is the baseband signal. It will convert to RF, the higher frequency, up conversion. Then after finally transmitting, you will have the power amplification and finally the radiation is there and this antenna is there. Similarly, at the receiver, we'll be having receive filter because in the receive you will receive the signal, so that will be the receive band, and at the receiver there's a low noise amplification, and the question is why low noise amplification is required, because whenever you transmit to a channel, the channel is corrupted with lot of noise. So you cannot you the receiver sensitivity, you cannot just embed the high noise message to before uh, embedding into hardware. You should have low noise amplification. Then again, the whole process is repeated, like we did the down conversion, RF to baseband. Then it is analog, since the physically occurring signals are analog in nature. So this is analog. So analog will be converted to digital. Then it will be match filter. Match filter are there to improve the signal to noise ratio, and this is maximizing signal to noise ratio. If I have taken the digital communication course, is to avoid or to reduce the effect of noise. Okay, and sometimes in practice it is a square root raised cosine pulse to give the best SDR, SNR. So you should know some of the terms like it is square root raised cosine filter. Then you will demodulate it, and finally you will again channel decode, error protection is there, then decrypt, and finally the source decoding. There are some basics of these two blocks, and there's one very good question. In I will just take that question also in our the problem session solving session. So suppose you are having the speech signal that is 8 kilo samples per second. Okay. So 8 kilo samples per second means 8 bits per sample. That is 64. Why 8 bits per second? This is 8 into 8 is 64. And this is kilobit samples. Sorry, this is samples per second or bits per second. This is samples. So here we're multiplying this bits per sample. So it is kilobits per second. In GSM, which is a 2G, uh, so we are having 12 kilobit via speech compression. So it's actually the speech compression. The compression block is here. So after source coding, it is having 12 kbps. Okay, so that is called voice coder, or also called vocoder. So error protection is what it is doing. So since I told that it will repeat the information, because at any cost we don't want to lose the information, so we'll repeat. And suppose the receive sequence is 101, so whatever the majority is there, the what that we will interpret it. So 2 are 1, so that's why it is 1. Similarly 8 psk, so this is 2 power 3. So we are having how much difference will be there in digital communication course if you have taken. So 360 degree divided by 8. So 45 degrees. So every symbol which is having 3 bits, because 2 power 3 is 8. So all the permutation and combination of that symbol, this is one symbol, will be transmitted. Okay, so this symbol will be containing some message, this symbol will be containing some message. So at the same time, we are able to transmit 8 symbols. That's how the spectrum is utilized. If you talk about BPSK, so then binary phase shift queen. So in that only two symbols are there, 0 and 1. So and the difference between these symbols was 180-degree. But since this whole constellation diagram is there, we need to utilize and we need to send as many symbols as possible. So we came up with M array PSK. M array PSK. So M is actually 8 here. So that's why it is like this. And there are some very good receive function that at the same time we need to do synchronization, because once we receive the message, the synchronization is very important. So you guys are asked before joining the session. So I'm changing the settings. Just a second. Accessibility. Meanwhile, you guys can introduce yourself. What is the motivation to join this course? Are you doing as part of your BTech, MTech? Just changing the meeting options. Okay, so I have changed this meeting option. Everyone can join this meeting. So far, excluding me, 8 people have joined. Uh, uh, Vinoj already introduced himself. Srinivas, would you like to
Yes, ma'am.
introduce yourself? Yeah, sure, sure. Please go ahead.
Yeah, this is Srinivas from RGUKT Nujvid.
Okay.
Currently, I was in BTech fourth year.
Okay, so are you crediting this course as
Yes,
part of
ma'am.
your curriculum?
Yes, ma'am. I am creating this course as part of my semester.
Okay, very nice. Okay, so
Already,
yeah, yeah.
I have some experience in 5G physical layer. So this motivated to me choose a wireless communication, wireless and cellular communication.
How what experience you have? Like in IIT Hyderabad also, we are working in 5G. Like it is very near, right? RG you told. Which college you told? RG? Where it is?
RGUKT Nujvid near Vijayawada.
Near
Rajiv
which?
Gandhi University.
Okay, okay. There are some students came from this your college for internship in my college. So I am from IIT Hyderabad. So there we are working in 5G. So you can also look into that if you want to join. That's fine. Uh, okay,
Yeah, okay.
Prabha. Prabha is not telling anything. Kartika. 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 She's also not telling anything. Kalyani. Kalyani. Asita. Okay, so you guys are not interested to inform about yourself. That's fine. Thank you for informing, Srinivas. Okay, so now you know these are already the part of our digital communication courses. Transmitter is there, for example, one mic is there. After mic, the source coding, encrypt, channel code, encode, modulation, pulse shaping, digital to analog, up conversion, power amplifying, transmit. Now, receiver also we are having, and we studied this separately in our digital communication course. So this course is all about the wireless channel. So we will be talking about the wireless channel, and in order to tell you, like it's very, very um, random in nature. That's why this course is all about wireless channel. Okay, so yes, so wireless channel are having three, four different parts that I would like to tell you. That it is having multipath, like it is not only a one part that determines from transmitter to receiver. So through multipath, some information is lost. Okay. At the same time, the signal strength fluctuation is there, which is called fading. And they are due to which there's a spatio-temporal pattern, which is very random in nature. As for that, the receiver must adapt to signal fluctuations. Okay. So I'm just telling you how the signals changes so much. So suppose we are having the 900 megahertz bandwidth. in 900 megahertz band, lambda is 1 by 3 meter. Okay, so lambda by 2 is 15 centimeter. So here this amplitude versus frequency, see how much it changes from this part to this part, even with the distance of lambda by 2, you can see the how only 15 centimeter. 15 centimeter is what? This much scale used to come, 15 centimeters. So in this range only, it's changing this much. So that's why the wireless channel has to be designed properly, and for that, we need advanced DSP algorithms to mitigate the time varying ISI. And there's a very well known receiver or the equalizer, which is called rake receiver. You should know this term. The equalizer is actually the rake receiver. And but at the same time, it is very computationally intensive, and equalizer complexity grows exponentially. So that is there. If we talk about the multipath and Doppler, so when we start moving, the Doppler term is suppose a vehicle is there and it is moving, and the transmitter is fixed. Then exactly the frequency of operation changes, and that how it changes, I will tell you through simulation. Then it causes a fading because it causes a signal strength fluctuation. The receiver must be adapt to time variation, and this is also called time varying ISI. And the rate of change depends on the Doppler. And whereas for this we need very much accurate channel estimation. Now you might ask why the channel estimation is needed. So if we don't know about the channel, then you cannot transmit any information. So that's why, in order to know the channel, the pilot signals are sent, which are known as a reference signal or the known signals. Once we send some known signal at the receiver, then through that known signal, we estimate it. And that estimation process is called channel estimation. But at the same time, the signal fluctuation is very used, due to which it causes this deep fade. Okay. So there are some concepts at which I am uh, trying to explain you. There's a wireless communications link budget, which says that suppose we are a AWGN channel, which is a receiver, receive of T is equals to transmit plus. Since it is additive wide Gaussian, why it is wide? Because it is affecting the same all the frequencies parallelly, and it is additive because it is additive in nature, and fading. So it is also having the fading information. This is alpha T. This 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 information is given by the fading, and if alpha T is very less, then the signal power will go very less, because SNR is nothing but alpha T mod square ST divided by noise power NT mod square. So the SNR should be high. So alpha T should be high. So whenever we talk about the fading per interference, so along with the fading, the some interference will be occurring from the same signal with different times. So the signal is ST, but at the same time, if there is some tau I difference is there, so previous tau I, there will be the interference. So this interference will be just inter-symbol interference, because the same symbol is there, whereas they are but different times. So it is inter-symbol interference, and that can be seen as like like this. Okay. Now these are some link budget. The link budget is actually how much transmit power we should use to have the to get the certain SNR, because certain SNR means, for example, a phone or any device or any radiating device, any transmitter, it should have a minimum signal to noise ratio, so that it can accept the signal. For example, it requires minimum minus 10 dB milliwatt, so that it will receive the signal. So every phone is designed in such a way that that is called receive sensitivity. Sensitivity. So the link margin is actually the transmit power minus receive sensitivity and some margins, which is primarily for the fading. So the key challenge is to have minimize the link margin as much as possible, and there are some formulas associated with it. For example, we are having the transmit power that is associated with effective radiating pattern, and including the antenna gain, because transmit power, so it depends basically on antenna. So and then we are having the path loss. Once we transmit, then it goes through path, so that path loss is there, and then it is Also a shadowing. Shadowing on path loss, what is the difference exactly is? So shadowing means if there are some reflector or some objects in between, so the signal strength changes. So that is called shadowing. And since through multipath and different ISI, there will be some fading. So basically, the fading is governed by the relay fading. And then we are having receiver sensitivity on finding the thermal noise. These are the terms that determine, and we need to minimize the link margin as much as possible. Okay, then I'm just moving wireless functionality in cell phone. Yeah, this is very important. Like it's FDMA, TDMA, CDMA. So in first generation cellular networks, we are having FDMA. Then in second generation, we are having TDMA. In third generation, we are having CDMA. The question why we use different type of multiplexing techniques, and whereas in 5G we are having OFDM, and in 4G also we're having OFDM. So these are the different things that is there. So I'm sharing my screen. Just a second. I hope my screen is visible. So to actually compare the time division multiple access and the frequency division multiple access, specifically, I want to show you why we changed from FDMA to TDMA. We focus on intersymbol interference. So the problem is like intersymbol interference in FDMA was more, and I will tell you how it was more. So the key concepts is like the users transmitted different time slots on the same frequencies. So the risk of ISI from the misalignment or the clock drift or the multipath will be where it will be more. It is actually in TDMA it is more, but still it's one of the technique that we use. Like different time slots are there for different users to communicate. Whereas the FDMA, the users transmit simultaneously on different frequency, so ISI is less critical. That's why in OFDMA, it's actually one of the form of FDMA where orthogonal users are used. So that's why the in 4G people realized okay in FDMA the ISI is less, so we need to use FDMA. But also at the same time FDMA it was more frequency was used because uh, different frequency slots or frequent frequency blocks we have to give to different users. So there was more resource constraint was there in FDMA. That was one of the reason why we moved from FDMA to TDMA, because frequency we have less. Okay, the frequency means spectrum. Frequency spectrum means resources. So that's why we moved to CDMA in 2G. But we again came back to FDMA. The OFDM is also one of the advanced form of FDMA uh, because ISI was more in 2G. Okay, in TDMA. So this example shows you why ISI was more in 2G. So I have transmitted a BPSK modulated signals and simulating the channel with multipart fading that causes ISI and also having the bit error rate. So this example gives me the bit error rate with the no ISI in FDMA was somewhat here, like here, whereas with FDMA with the ISI it was more, because obviously with ISI, if there is ISI, there is no ISI, then FDMA bit error rate will be less. So what is like TDMA is highly sensitive to ISI due to sequential sampling. Like in the same time slot will be used, so it is highly sensitive to the ISI, whereas FDMA is more resilient. But adjacent channel interference can still cause some errors. Here in this BPSK, there was no bit error rate. That's why, because only three symbols I have used. So here I have used yes. Huh. So here you can see the bit error rate with ISI in TDMA with no ISI. It is here. With ISI, it is greater than this, obviously. But in FDMA, either it is ISI or not ISI, it is very high. So our aim is to reduce the bit error rate. So this example, I'll tell you how this is drawn. So in Python, we are having NumPy, which is used for the arrays. Then matplotlib for plotting, and the SkyPy is used for some low pass filters and high pass filters and all those stuffs. So in BPSK modulation, we are having only 2 bits. So it is the modulation is like 2 into bits minus 1, and the demodulation is simply if it is greater than 1, then it is 1, otherwise it is negative, it want to return, so it will not be true, so it want to return. It will determine negative and positive. And if we talk about the TDMA, so it is like simulating the number of bits into number of users. The total number of bits will be number of bits per user, number of users, and transmit signal I'm just keeping as of now is the number of zeros, and then the transmit bit is like it's suppose I'm keeping the random from 0 to 2, the number of users, bit per user. Okay. For then after simulating this, like it's just some random values as of now. Now after like number of users, the modulation signal, every signal will be modulated as per the BPSK modulation function. Then we are transmitting that modulation signal and adding the ISI through multipath, like some channels I have taken, and through low pass filter, I'm passing that, and the transmit signal also I'm passing. The transmit signal is just is here. So adding the AWGN, the AWGN is nothing but the simple Gaussian noise. So that linear scales it SNR dB divided by 10. It is in the linear scale. The SNR dB is nothing but here I have determined through SNR dB, because SNR is nothing but signal by noise, S by N. So N I am trying to find it here. Then noise power is nothing but the variance of that divided by a sum of linear, and noise is nothing but square root of n naught into random values, which is depending on the transmit signal, square root y, because it is n naught. It's noise power I'm talking about. The receive signal is nothing but transmit signal plus noise. It's in dB as of now, so it is just we are adding it here with AWGN. And the receive bits is nothing but NP dot zeros, like it's again it's the same bits we are taking. Okay, so this we are doing as a TDMA for different time slots, because here we are doing the different time slot. And FDMA is something where we are determining a different frequency range. So again, the similar steps is followed for the FDMA. And I don't know how much you understand or not, but yeah. So here the carrier is added because why? With different frequency blocks, we are sending different messages. So different frequencies carriers are added, different frequency with for I uh, for different users. For different user, the different carrier frequencies will be added. And so again, the BER will be the number of received bits when it is not equal to transmit bit divided by bits per user into number of users. Again, simulating with different SNRs from 0 to 21 with a range of 2. We are plotting, and this results I'm getting. So this is one of uh, the scenario. What is the difference I'm trying to make you understand through uh, basically through simulation. And I'll come back to yeah. So as you can see, as the name suggests, we are having frequency division. So this is frequency division multiplex axis, and through this also I would like to explain you. Uh, so here in bandwidth, uh, delay spread, the delay spread, if you compare with respect to delay, so it is 2 to 5 microseconds. Okay. Delay spread means from one signal, if it is sent, the other signal, the delay between them is actually the delay spread that we basically look for. And in bandwidth, it is divided. Suppose we are having the 100 microseconds, because symbol time is equals to 1 upon bandwidth, that is 100 microsecond if the bandwidth is 10 kilohertz. So with different frequency, this is how it is changed. So 10 kilohertz, suppose it is 5 kilohertz, It is 5 kilohertz. The negligible delay spread is there. Whereas in TDMA, we are having suppose we are having symbol rate is in GSM basically. It is fixed 270.833 kilobits per second. And if the symbol time is 3.7 microseconds, so the message will be sent in for this 3.7 microseconds, and again the same overlapping time will be here, 3.7 microseconds. So it will start after 3.7 plus 2 microseconds. Then again it will start uh, 3.7 plus 3.7 plus 2 plus 2 microseconds. So every time it is adding. So if suppose we are having 10 Mbps of bandwidth, the symbol time will be 1 by 10. That is 1.1 microseconds. So zero point 0.1 microseconds. So how many symbols will be in ISI? How will you calculate? How will you calculate? So it is actually, how will you calculate the symbol to time duration? So symbols of ISI time, zero point 0.1 divided by, if suppose the 2 microseconds are there, then zero point 0.1, 2 divided by 0.1, it should be 20. It is not 50, it is 20. That's why it's written wrong. So 20 symbols will be in ISI. So there are some GSM frame structure. In 3G, we adopt code division multiplexes because here the user should not interfere. So different frequency will be used for different users. Here, time division with a different time will be used. But here in CDMA, we use different codes. Okay, so CDMA 3G is used, so that they should not interfere. The same frequency and time is there, but the different code is used. So spread spectrum technology, the orthogonality will not be in time frequency domain; it will be in different frequency domain. So here the signature sequences are used. Okay. So in what exactly it does is a message sequence or any message is multiplied with a spreading code sequence. And the spreading code sequence is actually orthogonal in nature. Okay. For example, the L chips multiply every bit, the bandwidth of the message will be increased by L. How? Because suppose we are using 4-bit spreading sequence and you are also having the message of length L. So 4 into L, 4L will be there, or 4 chips per second, because we are having 1 bit per second. You are using 4 chips. So it will be 4 chips per second. And but the disadvantage was that at the receiver it was very easy. At the receiver you multiply again with the same chipping sequence and you'll be getting the unique signal. So that's how you will be decoding it. So at the receiver, we will be multiplying with again same sequence, because the chip sequence or the chip codes are or orthogonal in nature, so that they will not interfere with each other. So that was the benefit of that. So they will not interfere with each other, but so that you can easily get every users. So it was very good until unless we identified that it is highly but it is taking high processing power, because we are having limited signature sequences. You cannot have unlimited. So that was one of the reason, like the processing gain was very high. So that's why we moved to again the FDMA. In 4G, FDMA is used. The OFDM is a beautiful form of FDMA where the orthogonal subcarriers are used. That's why it goes orthogonal frequency division multiplexers. That is OFDM. Okay. So in CDMA, for your information, Walsh Hadamard codes are used, and which is called as a spreading codes in CDMA. So I will just give you one example. We are having one. So using one, we can have one minus one. So if you, what is mean by orthogonality? So if you see one and one minus one, these are two different sequences. Okay. So if you multiply with 1 into 1 plus 1 minus 1, what is that? 1 minus 1, it is 0. So well, that's what. If f1 into f2 integration or dt from t is 0, then f1 and f2 are called orthogonal. Similarly, these are one vector, these are second vector. So vector 1, vector 2 are orthogonal. Similarly, these vectors, these vectors, these vectors, these vectors are orthogonal to each other. Similarly, this. But how many you can create? It's limited, right? So that's how the OFDM comes into the picture. Um, and at the same time, this was loss of orthogonality was there in multipath. So it was very difficult to maintain the orthogonality at every time. So that was there, and very difficult to have high data rate and spreading factor, and applicable to wideband CDMA, and it was also applicable to different HDSFA, high speed data packet access and different types, cannot simultaneously have high data rate and high spreading factor. So we want broadband system, no complexity of equalization, because at the same time it was difficult. We also have multipath. So FDMA is more robust if we can get rid of guard bands. So FDMA, as we know, we are having one, one, one. This was F1, this was F2, this is F3. How these frequencies are, right? This is one guard band. This is also guard band. It was good until now these guard bands are utilized. So how can we make sure that guard bands are utilized? So what if we use, so these are different subcarriers, S1, S2, S3, but the spectrum is same. So if we can utilize the orthogonal sequences or orthogonal subcarriers, then there's no point of guard band. So this is advanced form of this OFDM. That is. So orthogonalities also make sure ISI will also be not there. And how ISI is not there? Because in the OFDM process, I will tell you how ISI is not there. But the process of OFDM is like that. There will be no ISI. Okay. And also we finally find out we rectify the problem of CDMA, that we are having the limited signature sequences, and we cannot spread for very high data rate, because at the receiver we need to spread also, while when we are multiplying with the chipping sequence, we have to spread also. That was one of the issue that we faced. And so yeah, that's how the multiple access techniques are used. So it is OFDM, it is currently also utilized in Wi-Fi. These are 802.11, 802.1620, all are this in Wi-Fi. So like it is a effect of multipath. In CDMA there was a loss of orthogonality because of multipath, more severe if spreading factor is very low. Whereas in TDMA, need for very complex equalization was there, because we saw ISI is very, very high. How many symbols we saw in ISI in GSM? It was 20, right? So it is very, very high. It's more severe for higher baud data rates, whereas OFDM is attractive for high speed data and multipath fading. So it's a multi-carrier one, like narrow carriers, low baud data rate, long symbol duration is there, and attractive candidate for broadband wireless communication. Whereas opportunity to optimize coding and modulation. In fact, 5G also we have OFDM. It is used for WLAN, wireless local area network. These many technologies are used, and it is multi-carrier and multi-tone. So far we have read what is OFDM, and there's a long story about OFDM, how the OFDM works. I'll just tell you the block diagram of the OFDM. not in very detail, but yes. So we have actually serial data. So it converts serial to parallel. Then we are having IFFT. Then we add cyclic prefix. Then we add FFT. Then we have parallel to serial. Then we have cyclic prefix. Then again serial to parallel. Then we have FFT. Then yes, finally. So this cyclic prefix, this is a block diagram of OFDM. Make sure there is no ISI. Why? What it does exactly? Because we have having subcarrier spacing. So what it does is it takes some last part of the signal and add it here in the initial start. Again, it does for all the signals. It takes last part, it add it here. So what it does when we multiply it at the receiver, it it doesn't have any uh, common factor. So it makes the channel matrix as circulant, which it has some maths. I'm just avoiding here, which avoids ISI. This is all about OFDM. I think femto cells, reals, and all those things were there. Yeah. So in 5G, why 5G is introduced? This is because we are having lot of connectivity, so we need to have more advanced form of wireless technologies. So that's why 5G introduced. That is having high data rate, very crowds of users, mobility, low latency, which is anywhere, anytime, everywhere connected. That is 5G. Always sufficient rate is there, and there are some concepts of modulation that supports up to 256 com, and you should know this number. It's very very important. And so tell you one thing. Yeah. So and there's EB, that is the energy per bit. So what exactly it is? It is a power of transmit signal multiplied by duration of the bit. So one symbol of, if we talk about the QPSK, it is actually 2-bit, right? QPSK is what? One symbol. I don't know how much you are understanding, but yeah, first week was a little boring only, like it is completely theoretical. But from the next week onwards, we will have more engaging class. So if you are even feeling bored, you just ignore it for the first week. Um, so 1 bit duration is actually 1/2 symbol duration. Okay. So what exactly I'm trying to say? So the noise power spectral density is actually in the form of watt per hertz. So if you multiply noise power into bandwidth of the receive filter, because at the receive equation you might have seen the receive filter band. Okay, that first block was there because analog signal was there and receive filter band. So it is actually the noise power. So once we do this EB by N naught, it is PS by PN multiplied by TV into B equivalent. So what I'm trying to say is, and B equivalent, the receive filter band, actually inversely proportional to symbol time. So it is multiplied by TB by TS. Okay, and TS equals to 2 TB in QPSK. So the EB by N naught is actually the signal to noise ratio. It is bit energy bit is is actually minus by 3 dB, because 1 by 2, if you convert into dB, it is minus 3. So the bit error rate, okay, either EB by N naught. So always we get confused. That's why I wrote there for you to understand. This is minus 10, and I'm ignoring this theoretical part of 5G. You can go through that. There's last lecture, and even if you don't want to go through, you can just ignore for week one. But yeah, this I would like to tell you so that you never forget some steps. The last will start. Some notes are there. Yeah, I would like to tell you this. So it's minus 6. It is 16 com, so that's why it is minus 6. But if you say consider a wireless communication system using 16 com with A, if a data rate is 10 Mbps, then what is the relationship between EB by N naught and PS by N? So since the 16 com, each symbol carries 4 bits, so TS equals to 4 into TB. And as we know, EB by N naught I just told is equals to PS by PN of TB into TS by TB. And if you convert into dB, so 10 log dB is what? 10 log EB by N naught is equals to 10 log PS by PN plus 10 log, because it's multiplication. So TS by TB. And this is 1 by 4. So it is actually minus 6 dB. 2 is actually 3 dB. That's how it differs. See, same thing here it is written. Uh, the noise spectral density is actually watt per hertz, and noise power is nothing but and not into B. Please understand this. This is the difference. Also, there is one concept which is called C is equals to B log to 1 plus SNR. So what will happen if B tends to infinity? The question is, when B tends to infinity, do you think that C will also tends to infinity? Answer is no. C will be 1.44 S by N naught. And why? Because N is equals to N naught into B. So here you're having C is equals to B log 2 1 plus S by N naught into B. So here not only, here also it is B is there. So once we do the calculation, here you'll get this. I want this for you to guess this result as a homework. So this is homework. There are some full forms that you should know. I will tell you some full forms. So noise figure is actually in dB, and noise floor is all in dB. If they are in dB, they are multiplication, then you can easily plus it. So there's one very good term that is thermal noise. That is by default in by default available in any electronic device. In fact, you cannot mitigate it, you cannot remove it completely. Uh, that you don't know, you cannot also. So thermal noise is actually KTB. The K is nothing but Boltzmann coefficient. T is nothing but temperature. B is bandwidth of receive filter. So through this you can have the noise calculation, and N is directly proportional to B. Intersymbol interference is there, and also in cell sector, the cell size is hexagonal. Why? Because we need to utilize the space as much as possible. So these are the cells. And the rake receiver is the receiver technology used for handling delay spread in CDMA. So this is also important. And C is equals to mu lambda, we know. Uh, an example I will tell you about Doppler shift because it is very important. Mm. So in CDMA, actually, as I told, we have to generate the signature sequences to have the orthogonal signature sequence so that we can properly separate them in at the receiver. So Walsh Hada mod code in CDMA is used where multiple users the same frequency band simultaneously. To distinguish them, orthogonal codes are assigned to each user. The one popular family is actually the Walsh Hada code. The how to generate this Hada matrix is a square matrix whose entry is either plus one minus one and rows are mutually orthogonal. So in Walsh code, plus one or minus one are converted to binary format. It's just plus one and minus one is zero. So all code are used as a spreading codes in CDMA, ensuring this minimal interference. So construction is 2 power n is built recursively. It's like h of n, h of n, h of n minus h of n. So this is how with many types we can create. So this code I have written here. So it generates n cross n Walsh Hadamard code. So how it is there? If you remember, always you remember. H of 2n is equals to h of n, h of n, h of n, h of minus n. So it's a Walsh codes are generate this Hadamard matrix. Then later in order to convert it, h plus 1 divided by 2. So with any size you can create here. Later the minus 1 is actually 0 here, but you can have anything. So each row is actually the chip sequence. Either is row or any column is also fine. Assigned to a user in CDMA, these codes are orthogonal, meaning their dot product is 0. As I told, F1 into F2 should be 0. The application is again in CDMA. Each user multiplies their data bit by the unique hash code, which is also called a spreading code. At the receiver, the same code is used to despread and recover the original signal. Orthogonality ensures that signals from other users appear as noise, and other users will be not. If you multiply with other user signature sequence, you will not get the same one. That's how uh, the noise signals or the other users will be used. So h of 2n is nothing but h of n, h of n, h of n, or h of minus n. Hope you understand. Then other concept is Doppler shift. Like through Doppler, the shift in frequency due to relative motion between transmitter and receiver. For example, a vehicle is moving from one cell to another cell. So there is a motion. So suppose we are having the transmitter frequency as f and transmitter wavelength as we know, c, lambda is equals to c by f, where c is speed of light. So when the receiver is moving towards the source, which is approaching, so the relative velocity of the receiver is greater than zero. Whereas if it is moving away or which is also called receding, it is less than zero. So we assume the source is stationary only the receiver moves. So the effective wave front encounter rate is like suppose when a receiver is moved towards an incoming wave at the speed v(r), the receiver velocity. So each wave crest up, like as we know the basic physics principle. And so to the receiver slightly sooner, okay, because it will crest, okay, that in, signal is there. So in the receiver's frame, the effective wave speed toward the observer is c effective is equals to c plus vr. Okay, so since the spacing between the crest is still lambda, the receiver sees a frequency. Because what is the lambda? Lambda is the distance with which the peaks of the signal remains the same. Okay. Spacing between the crests is again the lambda because the lambda is not changing. The frequency will be C plus VR by lambda, and C plus VR by lambda is C by F. F will be increased by 1 plus VR by C. Okay. Again, generalizing to a moving source, suppose instead of receiver moves, as the source moves at Vs speed toward the receiver. So if it moves toward the receiver, so it pushes the crest closer. Crest, some I'm understanding or not, because the crest is the top part of the signal. So lambda dash will be C minus Vs by F. So how I'm telling that the receiver frequency is again here F into 1 minus Vs by C. Okay. If both are moving, then it is coming around F dash equals to F into C plus VR divided by C minus Vs. So with the small scale approximation for typical wireless communication where V is very, very less than C, we can linearize like C plus VR divided by C minus Vs equals to 1 plus VR by C into 1 minus Vs by S C. And that's how, if the Doppler shift, like the change in the frequency, Doppler shift is the change in the frequency, F dash minus F is nothing but F into Vs plus VR plus Vs by C. And since if the source velocity is zero, if it is zero stationary, then it is F into VR by C. So it is directly proportional to the velocity of the receiver in both cases. Okay. So if we have having suppose a receiver driving a vehicle, this one, and towards the 940 megahertz tower, like it's a base station. So this delta in the frequency is nothing but F is the current frequency, into VR, which is 16.67 milliseconds, divided by C. The change in the Doppler, the frequency it is, or the Doppler shift is 52 hertz. And these are some formulas. And if we convert, the Doppler shift is directly proportional to speed. That's how I'm telling you. And then again, the question was that will it affect the um, will it affect the bit error rate? So I want to understand from you whether it will affect the bit error rate or not. So the answer is no, it won't affect the bit error rate because it is only changing the frequency. So I calculated for the QPSK and it was not affecting it. These are some of my other results. So, okay, so finally, in order to uh, go to last part of of this class is finally I'll go through some of the questions. And these are the questions based on some last year problem solving. So we'll go from last. I like to start from last. So in a massive MIMO system, the beamforming is a concept of. So what beamforming does? So these beamforming was a part of 5G. So what happens in beamforming is we are having 1, 2, 3, 4, 1, 2, 3, 4 different antennas are there. So it is going this direction, this direction, this direction, this direction. So if we use the same antenna, the antennas together, so it will help to direct in a particular lobe, in a particular direction. So this concept is being utilized in 4G and 5G. So it's part of directional transmission and reception. The major application area of 5G is enhanced mobile broadband or ultra reliable low latency or a massive time. So its answer is all of the above. The communication receiver performs the following tasks, but in what order? So receiver, as we know, first it will do synchronization. Okay. Then it will do again in start we saw it was a source coding information and source coding and channel coding was there. So once we have the synchronization, then it will do the channel estimation. And once the channel is estimated, it will decode the channel. No, it won't decode because since it is channel and it is a receiver, so it will do the equalization. It will do the equalization. So it is first, the second, third, and it was fourth. So answer must be first, third, fourth, Second, channel decoding. Ah, yes. So you should know from the basic block diagram what it does. First is all it will synchronize it. Then it will do the channel estimation. Once it is channel estimation is there, it will do the equalization to remove the ISI, and then it will do the channel decoding. Suppose a cellular phone has 2000 megahertz of mega milliampere hour. Okay. Assume that the cellular phone draws 50 milliampere in idle mode and 200 milliampere, 50 in milliampere in idle, 200 milliampere during a call. Approximately how long would the battery last if the user makes 4 minutes call every hour? So, so what happens exactly is like in 1 hour first we'll calculate and then we'll calculate for 60 hours. Okay. So charge is actually current into time. How many charge is there? So current used in hour because here per hour is there. So let me check in hour. So during a call, it is taking 200 milliampere, and this is for how much time it is taking during a call because it is 4 minutes. So it is 4 minutes, and rest of the time it is ideal. Per hour we are calculating current per hour. In 1 hour it is 4 minutes. So 200 into 4 and plus how much? 50 milliampere into 56 minutes. It is in per hour. Okay. Current per hour. How long? So, time, since it will, if we calculate current, this will give some value, suppose x. So, time will be charge divided by current. Charge is, suppose it is coming to 60 milliampere, and charge is, as per this, charge is 2000 ampere, 60 milliampere. So, it is this value 34 R. I hope this question you understand. So what exactly it is asking? A cellular phone has this much of battery, which is charge. Okay. And charge is equals to current into time. Okay. And we are asking what is time. So first we need to calculate current. Okay. So current, how much time it is taking? So 4 minutes is there per every hour. To 400, 4 into 400, 200 plus 50, 50 into 56. And you'll get the current once you get the current. So that you'll divide here and you'll get the time. Only thing you have to make sure is, only thing you have to make sure is unit. Question number 12. Consider the GSM frame format as discussed in the lectures. The user assigned one time slot per frame and the gross data rate is 22.8 kilobit per second. What would be the obtained gross data rate if 6 tail bits are converted to data rates in addition to 114 data bits? So previously it was 114. So if we add data bit rate as 114 plus 6, so total symbols for availability of data. Okay, then what would be the obtained? So 22 tha, then it should be less or more. It should be more because data rate बढ़ गया. Now, based on that frame format, we have to check because it is written as discussed in the lecture. So I have to check how much frame format, what was the data rate there. So here in as per the solution, it is 120 divided by 576.92, and these values are coming from that frame structure. Consider a 4G device using 64 COM modulation, transmitting at the data rate of 6 Mbps. Nyquist pulse sampling is used. Duration of each COM symbol is. So 64 COM is there, 6 Mbps data rate here. So how will you calculate? What it is asking? It is asking duration. So you can calculate frequency of symbols. Okay, how will you calculate frequency of symbols? 6 Mbps into 2 power 6 it is. Yeah. So you'll be calculating 2 power 6 because data rate in bit per second is 6 Mbps. Whereas in 64, 2 power 6, 6 bits per symbol, 6 bits per symbol. So it is 1 mega symbol per second. Okay. Frequency of symbols I'm calculating. Okay. And the time symbol is 1 by f frequency. It is 1 upon m, 1 megabit, and this is 1 microsecond. This is how they have also calculated. Frequency of symbols is data rate in bits per second divided by bits per symbol. And yes. So multipart delay spread is the difference between the time of signal transmission and the time of uh, signal reception, whereas it is a difference between time of arrival of first and the last copy of the transmitted signal at the receiver. It is actually the difference between the time of arrival of the first and the last copy. So the answer is B. What are the next options? It's shortest signal between the time of arrival of two multipart components of the signal. No, not two multipart. It's actually the time of arrival of first and last. Now the question is: consider a 4G cell phone with a front-end receiver bandwidth of 20 megahertz and operating at 27 Celsius. The cell phone has a noise figure of 3 dB. If the receiver sensitivity is minus 125 dB watt, what is the minimum required SNR to rate the signal? So we'll calculate through link budget. So minimum required SNR is receiver sensitivity minus receiver noise floor, which is equals to receiver sensitivity minus receiver noise floor. So actually, tell me what happens is here. You have to understand this. So noise floor, as we know, it is KTB. Okay, and SNR is what? It is power by noise, right? So it is power. Receiver sensitivity is what? Minimum receive power. So it is minimum receive power. And noise power is nothing but and not into noise floor, noise figure, sorry. Because noise figure determines how much noise is there. Noise figure. So minimum receive power divided by KTB in the noise floor. And if you convert into dB, so what it is actually, SNR in dB. Maybe I have class in the still. I'll, I'll do after that. So minimum receive power in dB minus KTB in dB minus noise floor in dB. Okay, so minimum receive power is nothing but the receiver sensitivity, which is given here, minus 125 dB watt, and shear KTB and noise floor. So that's what it is written. So it's very confusing here. Just dB you cannot remember. Can you give me just 5 minutes? I'll come back. Meanwhile, please go through this. I will just come back in 5 minutes. Hello, so I'm back. So these were the questions on the last year week one. I'm trying to solve that question in front of you so that the same similar types of questions will come. At least you should know. And what do you say? So far, is it clear, Srinivas? Only you are there, I think, Kalyani.
Yes, ma'am, it's clear.
Thank you so much. So, okay, there are some different questions. So, you should know what is dB and dB watt, and dB means no unit. Okay, dB watt means what is the unit, and if you convert, it is called dB watt. And uh, if I say dB M watt. Suppose what is this? It is called dB milliwatt. So here I think sir wanted you to understand because it's very very important whenever we talk in terms of watt. So we should know that. So it is in the watt. How will we calculate the power level in dB watt? So it's just 10 log 10 power in watt and it is 10 log 10 power in milliwatt. So uh, you'll calculate and you'll get that. Milliwatt means how will you calculate in milliwatt? 1 watt equals to 10 to the power 3 milliwatt. So that's how 10 in 10 to the power 3. So 10 log 10 and it is 46 dB watt. And this is very, very important and very, very good question actually. If we have 4G phone, say in front end receiver bandwidth of 20 megahertz operating in this uh, temperature, the cell phone has the noise figure. So what do you mean by noise figure? Exact definition I'll tell you. This noise figure. So noise figure is actually a metric to quantify the amount of noise. So since it's just related to quantify the amount of noise, so that's why it is multiplied with noise power. So see, it's that's why when I was calculating this SNR, this is multiplied with noise power. Okay, so it is KTB into noise figure, and it is minimum receive power. And yeah, SNR is equals to minimum receive power divided by KTB into noise figure. And the question is, what is a minimum required SNR to detect a signal? Like a signal is having the receiver sensitivity. Sensitivity, matlab, if it is greater than receive sensitivity, then only it is required. So the minimum receive power, the receive sensitivity is dV watt. Okay, so it is minimum receive power divided by not in noise figure. This is how it is there. Huh. The seventh question: which of the following comments about statement one and statement two hold good? So yeah, fading causes fluctuation in signal strength. It is correct. The rate of this fluctuation depends on the Doppler. So what exactly the Doppler was doing? Doppler was changing, as we know, FD was what? The change in the is VR C by lambda. What was that? VR F by C. Some formula was there, right? Closed form equation. Even I get confused. Huh. VR by C. Sorry. Delta F is equals to F into VR by C. How to remember this formula is like this F is F. Okay, the same unit should be there, and VR by C will be cancelling at least their units. So yes. So the rate of this fluctuation, yes, it is depending on the Doppler. So I think the answer should be both are true. Correct. See, these are some theoretical questions that will be asked in your exam. So you should be able to answer at least this type of questions also, not from the week one. Gradually, we will move to the greater depth since this is week one. So I think it's not much importance to you, but it's fine. Uh, so if we say consider a communication system explained in lecture one, the pulse shaping is used for what was there? Pulse shaping, ISI removal, or improving the bandwidth, improving the efficiency. Pulse shaping basically was used for to fit the signal in a proper way. Okay, so it is improving the bandwidth efficiency, fitting the signal in the proper way. Okay, as I told. So question number 5. Consider the magnitude response of the signal xt as shown in the figure below. The real part is on the left and the imaginary part on the right. So what is the beauty of real and imaginary part? So as you can see, the real part is always even in nature. The odd part is the imaginary part is always odd in nature. So this is the phase spectra beauty, and this is the magnitude spectra. So what is odd and real, or real and odd? Sorry, even and odd. So the even signals are mirrored with respect to y-axis, and the odd signals are mirrored with respect to 0. So that is the benefit of this real and imaginary. How will you identify it as a real complex baseband signal, the complex baseband signal, real passband signal, or complex passband signal? So baseband and a passband difference is what? The baseband means that the base will be there. Since it is falling up to this part, so at least it is clear that it is passband. Okay. And the normal real signal have their even magnitude spectra and the odd phase spectra. So it is a real passband signal. Yes. The answer is written. The magnitude spectra is centered on FC. It is passband. As I told, it is centered on FC, not 0. So it is a passband signal. And the second thing is, as a magnitude spectra is conjugate spectra, it is real signal. Okay. It's conjugate symmetric. This is not correct. Like here, the main thing is a real signal is having the magnitude spectra as even signal, and the phase spectra is actually the odd signal that we can see. So a real signal is xt is equals to x of minus t. Odd signal is xt is equals to minus of x minus t. Also, the odd signal has zero origin. Okay, nice. So a 16 QAM constellation is given below. The average symbol energy is, how will you calculate? So average symbol energy is, if we calculate for every bit divided by number of symbols, okay? For all the bit energy divided by number of symbols or symbol energy, sorry. So in constellation diagram, the shortest distance is actually representing the energy. Similarly, for all of there are 16 symbols, so 16. So yeah, how this is calculated. Distance is actually the energy here. There are 16 symbols in the constellation. The energy of each symbol is given by its distance from the origin. We observe that there are 4 symbols at 2 unit distance from the origin, 8 symbols at the 10 distance. So we have to just calculate, sum it, and divide by 16. That is 10. That calculation you can do, but the idea you should know, the distance is actually the energy governed by every symbol. Mm, And the question number 4. Okay, question number 4 is done. Using a 8 PSK modulator turns 2 power 3 bits into symbol. I was telling that in the class also. Okay. The audio signal is one-sided bandwidth of 12 kilohertz. Sampled at Nyquist rate, okay, quantized into 8 bits per symbol. The data rate is bits per sample into sampling rate.
Hello, ma'am.
Yes, yes, yes.
If I am not wrong, the distance is root of ES. According, I have studied root of ES.
Yeah, it should be square. Distance is equals to root of ES. ES is equals to D square. No, I think it is D. It is D only, not root. Let me check. Uh, Distance from constellation. The constellation point is energy. No, it is D actually. In fact, then it is wrong. I have to check. No. Distance between two constellation point is 2 root of EB, but the energy of each symbol is distance square. You're correct. It is distance square. It should be yes. It should be distance square. Or I will check and let you know. Even I am confused in this. Is it a distance or it is a distance square? Okay, Srinivas, next class I can tell you that. But yeah, you are also correct. It was distance. Can you also check in the internet?
Uh, as per as my knowledge, I have recently get into the gate coaching. I have seen that root of ES. I think so.
Yeah. Yes. So it is wrong here then.
Yes, ma'am. I think so. While calculating probability of error, distance is root EB is root EB by
Yeah.
n naught. So we replace D12 whole square, something like that.
No. EB is directly proportional to ES. So if ES is EB is D is equals to I remember D is proportional to EB. So EB is directly proportional to D square, right? ES is also directly proportional. It should be square, or maybe by I don't know why it's said has given solution in this. I have to check, and please I'll let you know in the next class for sure. Maybe uh okay, I will let you know. But here they haven't taken the square in the solution. Just the energy of symbol is given by its distance from the origin they have written. It should be distance square. I will let you know, please. Yeah. So the data rate is actually bits per sample into sampling rate, and sampling Nyquist rate is 2 into the actual bandwidth, which is 2 into 12 kilo samples per second, 8 bits per sample, so sample per second. Just sometimes you by unit also you can go to it because data rate is the bits per second. So bits per second, how will you get? It's bits per sample. So bits per sample it's already given, and then samples per second is in the Nyquist rate. So that you will get to know. And the first question is like determine the Nyquist rate for this signal. So we have to find 1 plus cos 100 pi t, as you all were telling that you have done the gate course. Then find 200 pi t. So highest frequency is 2 pi by 200 pi. Sorry, 200 pi divided by 2 pi. It is 100 hertz. So Nyquist rate is 2 into f. So it is 200 hertz. Highest frequency 2 into FM. So that is the Nyquist rate. So yeah, so far we have covered some concepts of week one, and we have solved previous year week one assignment. So Srinivas, have you gone through the assignment of this year? Like the questions are different.
I have gone up to lecture 4 only, ma'am. I have not entered into the assignment one.
Okay, so mostly the assignment questions are different, and that you have to solve. So my aim is to just help you in solving some of the questions. So still, if after that, if there are some doubts in solving the questions, I am free to just uh, interact with you. So I think we can end this class as of now. Thank you so much for joining, both of you, Kalyani and Srinivas. We'll meet in the next week. Every week we'll be having this class from 3 to 5. So again, some 5, 10 minutes are there. If you want to have any doubt, you can just you can ask me any doubt. And yes, if there are no doubts,
Ma'am,
then
where can I
yes,
find the collab files? Collab files.
yes. I will share that files also. This file also I will share. I will share maybe in the Google Drive. Is that drive shared with you?
No, ma'am.
That file will be shared with you. I think I will share mostly in some of the sheets they must have given me. So that only I will share. So I'll let you know if there are some things uh, which is not clear. Then I will let you know. This first class I will let you know about that. There must be some sheet. Every time it is the sheet, Google Forms. Okay, sure. I will let you know about that. But I will share both of the lectures, and I think these slides are available to you.
Yes, ma'am. They are available.
Then it is good. If that is available, then it is very good. Then yeah, I don't think so. The questions and answers are available to you. The last year questions and answers, is that also available?
No, ma'am. Not available.
So okay. So I will share that question and answer and the collab file soon in the drive folder. It must be there somewhere. Where it is located, I will let you know about that. Thank you so much for
Okay, ma'am.
joining.
Thank you.
Yeah. Okay.